Hello and welcome to another episode of Monday Night Calculus. Your questions, our responses. I'm going to change that to our responses on the fly here, but it says our answers. Steve Kokoska, Tom Dick are joining me here. My name is Curtis Brown and I'll be hosting this evening. Really excited for the content that Steve has spent some time collecting over the past couple of weeks, looking for your questions out there. We are certainly watching for those. And before I turn it over to these guys, I kind of make this plug every week, and I think I'm going to continue to do so. Really excited to ask and invite you to get your students involved as much as you possibly can in these sessions. I think it's beneficial. We've had several students join us in the past couple of weeks and had them asking questions, and I think it's really good for them to be exposed to these guys and their knowledge and getting information from other credible sources. So I think that's an awesome thing for you guys to be able to take advantage of. So hopefully this is a great resource for you. Welcome, Sarah. Super excited to see that you are here this evening, joining for the first time live, and not having to watch it at 4 a.m. Tomorrow morning. So glad that you're being able to see it live right now. So Steve, I'll turn it over to you. Looking forward to this evening.
Well, thank you very much, Curtis. It is a pleasure to be with you and Tom once again, and Allison in the background. We've got some great stuff, I think, tonight. We've got a couple of multiple choice questions that we're going to start out with. We've got an implicit differentiation question. We've got a derivative of an inverse, and with a little bit of luck, we'll end with a particle motion problem. So I think we've got some really cool stuff. And Curtis, I'm going to put you on the spot. I'm going to be asking you some questions again tonight. I'm sorry about that.
Uh-oh. Well, if I can't answer them, maybe folks in the chat can help me out.
All right. Very good. So this one starts out and says, if f is a continuous function for all x, and if it has a relative maximum over here at -1, 4, and a relative minimum at 3, -2, this one asks, well, which of the following statements must be true? You know, when you think about this, this is kind of a typical AP multiple choice question. The only drawback here is this is a couple of years old. If you take a look here quickly, there are 5 possible choices. And as we all know, this has been reduced to just 4. But nevertheless, this is a great problem to have your students practice on. This one was in the Facebook group, I think, written by Rachel Elaine, if I've got that correct. And what I did to start this out, and I'm going to try to use this, see if I can sneak this in here. I drew a graph here down at the bottom. I'm going to add a little bit to this, but I'm going to try to use this graph to determine which of these statements must be true. So the first one says the graph of f has a point of inflection between x = -1 and x = 3. Well, wait a minute here, wait a minute. This is my relative maximum. I think I've got that correct. And over here at 3 - 2, there's my relative minimum. And I drew a straight line connecting those 2 points. And you may remember, Curtis, back a couple of shows ago, we talked about concavity.
Mm-hmm.
In fact, that straight line would have no concavity. So there's no inflection point in there. Now, if you don't believe that, if you don't buy that, I could, if I really wanted to, I'm going to try this, Curtis. I could draw a curve like this. Whoops, I'm sorry about that. There we go. That's not too bad. Between -1, x = -1 and 3, I'm going to argue that that curve is concave up. And so certainly there is no point of inflection.
Right.
So A doesn't have to be true. All right, let's see. F prime of -1 is 0. Well, let's see. If f prime of -1 is 0, what does that mean? The tangent line must be horizontal. But the way that I've drawn my graph, there's a sharp corner at x = -1.
Right.
And as we've talked about before, if there's a sharp corner there, that means the derivative does not exist at x = -1. So this one doesn't have to be true either. All right, the graph of f has a horizontal asymptote. Jeepers, what does that mean? Well, as x goes off to +infinity or x goes to -infinity, that means that the value of the function must be approaching some fixed constant. Well, this problem here in the statement of the problem, we don't know anything at all about this function as x increases or decreases without bound. And in fact, the way that I've drawn this goes on and on forever up here to plus infinity. This goes down to minus infinity. There's no horizontal asymptote there. This satisfies all the two requirements given to me. So it doesn't have to have a horizontal asymptote. The graph has a horizontal tangent line at x equals 3. Well, okay, this just makes the student think a little bit differently here. That would mean, if that's true, let's see, where's the pen? There it is. F prime of 3 would have to be 0. The derivative would have to exist at x equals 3. And again, I've drawn a sharp corner in there. So the derivative does not exist at x equals 3. So that one doesn't have to be true. So it looks like we've ruled out the top 4. So E's got to be true. But you know what? We better check this. It says the graph of f intersects both axes. Well, I'm going to do the x-axis first. Now, the way that I've drawn it, it intersects somewhere between 1 and 2. But the question is, how do you know that it must intersect the x-axis? We'll get to the y-axis in a minute. But how do you know? Curtis, maybe that's one we could throw out there for the chat.
I think that's a great one to put out in the chat. And we do experience a little delay every once in a while with the chat. So we'll wait for that to go across.
While they're thinking about that one, I'll talk about the y-axis.
Okay.
So for the y-axis, we're told here that f is continuous for all x. So we certainly know that the function f is defined at x equals 0. Since it's continuous, we can't have f going off to plus or minus infinity or anything. It's got to cross the the y-axis somewhere. So the graph intersects both axes, and I'm still waiting for a reason why it must cross the x-axis.
We're getting Jenny Foreman and Ruth Ellen are both saying the IVT.
Ah, excellent. IVT, right on the nose. Excellent. Fantastic.
Good. For the non-calculus person in me, that's the intermediate value theorem, right?
Very good. Very good. Yes, very good. Okay. Excellent, Curtis. Let's take a look at number 2 before I hand it over to Tom here. He's going to do some technology in a minute. This is another nice multiple choice question, I think, and a little bit different. This time we're given a function f, and the derivative satisfies this equation. I hope you can see this on the screen. This is an f over here, and this is an f prime on the left-hand side over here. And this is another one that says, which of the following statements must be true? Now, I don't know about this name. You know, this may be a combination of a couple of people, but that's the way I copied it out of the Facebook page. So I do want to give credit where it's due. That's the person or persons who posted this one. And let's see if we can figure this one out. The first one says f prime of 0 is equal to 1. Well, let's see. I've got this relationship up here between f prime and f. I've got an equation for f prime. So what I did is I plugged in x equals 0 up there. And let's see, there's a 4 times 0 to the 4th. There's f of 0 squared, 2 to the 0. Okay, let's see. This expression is 0, so that's gone. I don't know what f of 0 is. And 2 to the 0 is 1. So are we absolutely positively sure that f prime of 0 is equal to 1? We can't be, because we don't know the value of f of 0. It could be 0, but we don't know anything in the problem. We're not given any extra information in the problem that guarantees that. Cool.
So just a heads up, Steve, Ruth is actually on the call tonight, on the video tonight.
Oh, good. Very good.
Yeah.
Excellent. Excellent. So that one's not true. Okay, the next one says that f of x is greater than 0. Now, I've put a question mark down here. We're not really given any extra information about f. I have a feeling why this distractor was put in was because of this expression over here on the right-hand side. Kind of as a distractor, but we don't have any information here about f of x. We can't draw any conclusion about its sign. So That one doesn't need to be true. All right, let's see. The tangent line to the graph of f at every point has positive slope. Well, let's take a look at this expression once again. Here's the expression that was given to us. Oh, this one looks pretty cool. X to the fourth times 4, that's always positive. F of x squared, that's always positive. And let's see, 2 to the x, that's always positive.
Always positive.
So this is always greater than 0, which means the tangent line to the graph of f at every point has positive slope. Now, I think a subtle point. Go ahead. I'm sorry, Tom.
So I'm going to be a little. I'm not going to contradict your conclusion, but I'm going to be a little bit picky about it. I would say that those first two terms, they're definitely non-negative.
Right, absolutely.
It's just slightly different than positive, right?
Could be 0.
Right, could be 0, but your 2 to the x, that tips the scales. Now we know we're for sure positive.
Yep.
That's really a good point,
Excellent
Tom.
point. Yep.
Good catch on that.
So it sure looks like C is the one that must be true. But let's check this. F is not differentiable at 0. Well, let's see. We already took a look at that up top. Oops, I'm sorry about that, Curtis. Where'd that go? There it is. We already took a look at f prime of 0. There it is. I think I rewrote it down below here. Here it is. We've got an expression for f prime of 0. We know that f of 0 exists. I hope. F is a function satisfying this expression for all x. So we know that f is differentiable because we've got an answer. We've got an expression here for f prime of 0. And it is differentiable. So this is not true. Boy, there's a lot of knots in there. And it's not none of the above because we found that C is true. How about that?
So the interesting, Ruth put into the chat here that she also saw that in her copy of the question, it looked like, or it appeared to be f squared or f raised to the 2 of x, which could be interpreted, or it looked like it might be interpreted as a second derivative, which kind of made that look a little bit confusing.
Gotcha.
In the notation maybe. So seeing it written as f of x squared makes it significantly clearer.
Good. Very good. Okay.
Welcome, Michelle. I'm just calling out Michelle joined us here for the first time. Fantastic. Hopefully some of your students do join. Michelle, thank you for joining us this evening.
All right, this is a good one. It's got 4 parts. Curtis, when I'm done with this, I'm going to turn it over to Tom for some technologies. There's a lot of cool things going on in here. A lot of nice AP calculus concepts, I think. Let's consider the curve given by this equation. Notice that that is sort of an equation in x and y. There may be several sort of functions defined implicitly by that equation. In part A, it says show that dy dx equals that expression. I might just remark that, we've seen a lot of these on the free response portion of the AP calculus exam. They kind of switched away from saying find dy dx because then there would be other parts of the problem that asks students to use dy dx. And if they found the wrong one, it made scoring it very difficult and awarding proper credit difficult. So this way, we're asking them to show that, and they have to show enough steps to convince us that dy dx is equal to that expression. So, okay. I'm going to take the derivative of both sides with respect to x. I am treating y as a function of x. I apologize, I don't have everything up on the screen here. So I start at the outside, and I work my way in. This is 3 times the inner function raised to the 2nd power, derivative of the inside function. 2 times y prime. I'm going to write it like that just to make it a little bit easier to work with. Derivative of 24x with respect to x, just 24. Derivative on the right-hand side, just 0. And the rest is just a little bit of algebra. I think in the first step, I brought the 24 over to the right-hand side. I divided both sides by this expression, 3 times 2y plus 1 squared. I did a little bit of simplifying here. I think I was able to take out a 3 out of both of these terms. And then finally, I just divided both sides by a 2, and I did a little bit more canceling. And son of a gun, did I get the right answer there? I did. There we go. Interesting about this problem here, and we'll see this as we go along because it's something a little tricky later on. Notice that in this problem where we take the derivative implicitly, we have an expression for y prime only in terms of y. There's no x on the right-hand side. And that seems kind of strange for those of us who have been doing derivatives, and we always find f prime of x in terms of x. There's no x's on the right-hand side, but that's okay. I think we've done everything correctly. All right, the next one said, write an equation of the tangent line to the curve at the point -1, -2. Well, look, I'm just going to verify first that -1, -2 is on the curve. I just remember my college calculus professor. He was a sneaky guy, and he put one of these on an exam once where the point was purposely not on the curve. So I checked it. Now, I know that the AP calculus program would never do anything like that, but I just checked to make sure. I need to find the derivative. I need to find the slope of the tangent line at that point. So I think this notation is okay. I want to find the derivative at the point where xy is equal to -1 and y is equal to -2. I don't have to worry about that x value of -1. Remember, this is 4 divided by 2 times y plus 1 squared. And let's see, did I do that simplification right? I think I've got a 2 times -2, that's a -4, plus 1 for a -3, square it. Yep, got a 4/9. I need an equation of the tangent line. There it is. Y minus a -2 is equal to 4/9 times x minus a -1. I get this, Tom and I get this question frequently. Look, on the AP exam, if they ask you for an equation of the tangent line, can you leave it like that? Yes, absolutely. That's fine.
Yes.
If a student goes on and tries to solve that for y in terms of x, get y all alone on the left-hand side, and they happen to make an error, an algebraic error, a mathematics, a simple error, then they would lose that point.
Yep.
So
this is why I have a soapbox for point slope form of a line in any kind of form that you come up with it, right? In this form where you've got things on both sides of the equation, and if you've got it in more of what might look like a transformation, I'm a big proponent of that. And while I've got everybody distracted, I also want to just welcome. There's more students that have joined us this evening. I've got Ronan and I've got Terry also joined us this evening. So really excited that we've got some students joining. So ask questions, guys. If you got questions, fire away.
Terrific. Well, you know me, Curtis, I wanted to check this one graphically. And so I kind of did this blindly, and then I had one of those, she moments here. I graphed this curve, this expression in blue here. That's a graph of the curve given by that expression. And I didn't expect to see anything like this because, I figured that y is given implicitly here. And I thought, well, maybe there are 2 or 3 or even more functions sort of defined by that expression. But in fact, there's only one given by that expression. So if you'll allow me, I'm going to sneak back up here for a minute, take a quick look at this. You can actually solve that expression for y in terms of x. So you could do that algebraically and produce the same graph. Anyway, here's the graph. Here's a graph right here in green of that tangent line. Here's the point. Whoops, I'm sorry about that. Here's the point down here. Let's see, what is that? -1, -2. And the reason that I did this is because I just wanted to see if everything seemed right. Does that line that I drew there, does that look tangent to that curve at that point? And yes, it did. Now, I didn't draw this in a nice aspect ratio of 1:1, but I still feel pretty confident. I still feel pretty good about that graph. Cool.
Yeah, that's a good one.
All right, here's another one. This is nice too. This one said, look, let's find the second derivative and evaluate that at the point -1, -2. Okay. So I went back to y prime and I said, well, look, I got to take the derivative of both sides. I got to find d squared y over dx squared. And I looked at the right-hand side and said, well, you know, I could do that using the quotient rule, but I think that would be long, harder. And so what I did is I converted that and wrote this as 2y plus 1 to the minus 2. I thought that would be a lot easier. So the second derivative is the following. Here's the constant 4. Bring the minus 2 down, times the inner function raised to the power minus 1. There's the minus 3. Times the derivative of the inner function, which is 2 times y prime. Now, I'm not done. I got to get rid of that y prime. Now, and the truth is here, I'm going to throw this out here. Curtis has another question. I think Tom will help me on this when he gets to technology. I don't think I really have to get this all in terms of y to get my final answer. And let's just throw that out there as a question as to why not. But I did. I have an expression for y prime. There it is. I did a little simplification and ended up with this expression. Notice once again, just kind of flukily, the second derivative is in terms of only y, not x and y. Okay, little bit of algebra here. I plug in x equal minus 1, y equal minus 2, but wait a minute, there is no x in here. There's the y value, a little bit of simplification. And I think I got a 64 over 243. That's pretty cool. So why
really
don't
interesting question that you continue that you're still having only in terms of y.
Yes.
That's very interesting.
So why didn't I have to do this? Did I get an answer to that one?
I haven't seen anything that says why you didn't have to do that.
Okay.
That piece there.
Okay. We'll leave that open for the BMW tonight.
All right, that's
Okay.
fair.
That's fair. Okay. Part D is nice here. This invokes this idea about the derivative of an inverse function. And I thought it would be kind of useful if I just kind of restated this formula, you know, and I get this question frequently, you know, do students have to memorize this formula for the AP exam? You know what? There's almost always one question, at least in the multiple choice portion of the exam, that asks about this. So yeah, this is one that they have to know. I'm not going to derive this with you. There's some nice graphical stuff going on, and maybe Tom will show you a little bit of that. But let's see if we can use this. And I apologize for this. This notation up here is in terms of F and F inverse, but I'm really going to use the symbolism or the notation that was given to me in this problem, which was Y and Y prime and Y inverse, okay? So this problem, part D, actually involved another point, if I've got this right. It says that 1/6 and 0 is on the graph of F or the graph of Y. That means that 0, 1/6 is on the graph of the inverse. Okay. So let's see if I've got this right.
Yes.
If I want Y inverse prime of 0, that's Y prime of Y inverse of 0. Well, wait a minute. Y inverse of 0 is 1/6.
Yes.
Okay. Now I'm going to separate this out. I understand this is a 1 divided by an expression. I'm just going to take a look at this expression first over here. This is the tricky part, I think.
Yeah.
Okay. Y prime of 1/6. Well, wait a minute. I've been using this expression for Y prime in several places already tonight. So it's 4 divided by, and here's the tricky part here, 2 times Y plus 1 quantity squared. So the desire here is to put in a 1/6, but that's the X value.
Oh, wow. This is a sneaky one.
Isn't that sneaky?
This is a really sneaky one. And there's been some comments now in the chat here. One, to your question in part C, it's the second derivative. They only asked for the second derivative. And so that's why you didn't really have to do the part.
I don't know about that.
Is that true?
I need to find this value. But what
Right.
okay, so what my argument is, well, look, I simplified all the way to this.
Yeah, but you didn't have to. You could
My
have done the
claim,
left-hand one there.
my claim is, I think I could have actually just left it right here and got an answer.
Right, right.
And I think the reason is because I actually have y prime evaluated at this point up above.
Right. So
Okay.
then the other piece of this, and Jenny called it out, was that it's pretty sneaky that a lot of this is only in terms of y.
Indeed.
And so the temptation to plug in that that value of 1/6 there instead of the 0.
Yep.
Yeah, that's a good one.
Okay. So I'm going to take that value of 4. Okay. And then I'm going to put it back into this expression here. And so y inverse prime, if I said that correctly, at 0 is actually 1/4. Now I'm going to turn it over to Tom, and I'm going to, as I do that, I got this answer, Curtis, and I kept saying, oh, this can't be the right answer. This can't be right because, wait a minute, up here in part B, I got the slope of 4/9. This can't be the right answer. It's got to be the reciprocal. But no, that's not right, because I'm not looking at the point -2 -1 on the inverse. This is a completely different point down here, 0, 1/6. So that's where I thought this problem was going when I started it. And when I started to work this out, and wait, this must be the wrong answer, but no, it's correct. All right, Tom, I think there's some technology in here. Can I turn it over to you?
Sure, that'd be fine.
All right, there you are, sir.
Okay. So I was going to try to pick up right off where you left off there, Steve, with that part D, and look at some things on the TI-84.
Okay.
So let me share my screen and see if I get the right thing up here. And you guys can let me know if I've got my TI-84
Looks good.
on. Okay, fantastic. There's not an implicit grapher on the TI-84, but in this particular case, as Steve pointed out, we could actually solve for y explicitly. So that's something I wanted to do here. But the other thing I wanted to show is in part D of this question, Steve was having to deal with an inverse function. And even if you have an explicit function, if you're looking at an inverse relationship, it might be difficult to plot or hard to solve for that inverse function. Mm-hmm. So I wanted to show kind of a neat, easy way to plot inverses on the 84. Now in this particular case, first thing I want to do, I mean, if we went to our y equals menu, this is what we're used to seeing, the y1, y2, and so forth. But I'm actually going to switch gears a little bit here, change my mode, and go to parametric. So I just scroll down here and change the mode to parametric. And now when I return, yes, Curtis, did you have a?
Sorry, I shouldn't be muttering to myself in the background here, but I think I know where you're going. And I just said, Tom, that's genius.
Okay. Well, clearly I didn't come up with it. I got it from someone else. So now what I've got here is I went ahead and solved for y in terms of x. And it wasn't too bad. You know, it was just adding 24x to both sides and taking the cube root and just kind of unraveling it. But you'll notice what I did was I've gone into the parametric plotter and made my x1t just equal to plain old t. And then y1 of t, I've replaced x by t. So this is what you would get if you solve for y in terms of x with t replacing x. And I want to plot this parametrically. So let me go to my window. And I think that I've tried to put in a window. Notice I've got a tmin tmax, which is not a window dimension, but it's my parameter domain. But since t is matching up with x, I went ahead and made it -4 to 4, which seemed to be what Steve had on his graph. And y-min to y-max was -3 to 3. And so there's my window. And let's take a look at this graph parametrically. Sure enough, I think it's almost even the same color as Steve. So we've got that nice graph. And if you turn on the trace, you actually get all three values. You get the x and y coordinate, but you also get the parameter value t. And so we can trace along there. Let's see, I think one of the points was, is it -1, 2? Or -1, -2?
Yes.
There we go. When I trace to t equal -1, there we are at -1, -2. All right. Okay, so here's where I'm headed with the inverse is I want to go back to the y equals menu. And we're going to plot the inverse now, but it's going to be really, really simple because all we're going to do is interchange the x and y from that first parametric. So I'm going to make x2 of t. Well, let me go to my y variables, to the parametric. I'll make x2 of t the same as y1 t. And then I'll make y2 just regular old t, like that. So I've just swapped the x and the y. And we get a beautiful graph of the inverse. You can see that that symmetry with the line y equals x. Actually, the window I have here is not perfectly square like Steve's, but you can get the sense of it. And another kind of cool thing here is if we trace, it starts at the very first t value, but if I wanted to jump to a t value, let's see, I think, Steve, your point you were looking at was 1/6, comma 0.
Yes, right.
Yeah, 1/6, comma 0.
Well, I'm just going to put in t equal 1/6. Oh, there we go. 1/6, 0 is on the graph. And if I use the up or down arrow, what that does on the tracing is it cycles through the functions. And if you only have two, I said function, I should say two pairs of parametric equations, but it's going to toggle between the two. So if I toggle over to the other, notice there, let's see, did that do what
it's your trace step. It's your T step.
Okay, so I need to go back a couple there. Okay.
You'll have to choose that, yeah.
Okay, so this should be, let's see.
We want to find, I think, 0.1/6 on there.
0.1/6.
Right. Okay. Well, that's
a little to the right, maybe.
So,
well, let me just type in 1/6 again for t.
Okay.
There we go.
yeah, I was just going to suggest that. So
yeah, I was going to say,
something to be aware of.
Y values, so that's good.
Right.
That's good. Yeah. Sorry, I just I was thrown off a little bit there when it advanced the t increment unexpectedly on me.
Yeah, that's the rounding on the t step. So if you think about if you wanted to, prep this particular question, you could have gone into the window and set it up to go by units of 1/6, and then you would have nailed it on the dot. But Tom, what I'm just gonna, while I've got you interrupted, I'm just gonna say that first of all, I had never seen this before. That's brilliant. What a cool idea. And secondly, now just from a teacher perspective, if you go back, because of the way you defined the red equation here, if you go back to your y equals menu, I can use this to work with any other number of inverses that I solve for for y in terms of x, and I work it out, and I can work this for any number of these different things. And what a brilliant! I'm just giving you lots of praise here tonight, Tom. What a brilliant teaching idea, and nice exploration. Cool.
So I did want to point out one other thing that we've got going for us here is, let me go back to the graph, is if I, if I'm tracing there, let me go to that point. Let's see, this is on the blue graph, the original, I think -1, -2 was one of the points we had, and we were interested in tangent line. Well, to get at that, you would need to, calculate the slope of the curve at that point. If we go up to calc, that's the shift of trace, we notice we can either calculate the value of our parametric there, or we can do any one of these three derivatives. The dy dt and dx dt, of course, those are of our individual coordinate equations, but dy dx will be the actual slope of the curve. Let me go down there and evaluate that and hit enter. And I believe, Steve, you ended up with 4.9.
Correct.
Well, that's sure looking like the decimal, a little bit of rounding there, way over there in the 7th decimal place, but
Yep,
that's
good.
reassuring. If I toggle over, let's see, this would have been
Perfect.
Yeah, that's
do we do
right where you need to be.
And then we want to do the slope there. We should get, and this is where Steve was expecting to see 9/4. Whoops, let me
You are wrong equation.
try that
There you
again.
go.
All right. Keeps
You'll
going
need to
back
up arrow to the.
Okay. Oh, got it.
There you go.
Now I'll hit enter. 2.25 is really wide, which is 9/4.
Yep.
Thanks for the assist there, Curtis.
No problem.
Very cool.
All right. So I think I probably should turn it back over to Steve and
Okay.
on there.
Man.
Let me stop my share here. All right, somebody can.
I'm going to use that trick trick. I hate to call it a trick. I'm going to use that strategy in a future conversation for sure, because that's just that's really nice for plotting inverses that way, Tom. That's pretty cool.
Beautiful.
Okay. All right, I'm handing it back over to you, Steve.
Okay, thank you, Tom. Cool stuff. Curtis, it's kind of neat to follow this Facebook page, because you can see as people, as teachers are making their way through the curriculum, how the questions sort of change.
Yeah, for sure.
This is kind of cool.
Well, that's what we were hoping when we came up with this idea of doing this your questions, our answers idea, was that we would have this ever evolving sort of set of questions, both from teachers and students, to be able to talk about.
It's very cool. And this is a good one. This was posted, I think, by Rick, Eileen, Aaron, which sounds like it could be 3 people, but I don't know. But that's the name that was associated with the post. And this is a related rates question. And I have to say that I edited this just a little bit. I hope to make it a little bit clearer. This one is kind of prescriptive with a little twist in there. So we have sand falling from a rectangular box. The box is 40 by 20 inches. And the sand is emptying out of this box at a rate of 300 cubic inches per minute. Of course, all of us know that we have to be careful about units in AP Calculus. So the first one says, find the rate of change of depth of sand in the box. Okay, so I'm going to sneak down here to part A. So I think what I did is I wrote an expression for the volume of the box. I know that it's 40 by 20. But I don't know the depth. So I use this value D. And I apologize for this, Curtis, but every once in a while we see these couple of D's together, a small d and a capital D. I think of the volume D and the depth D as being functions of time. I take the derivative of both sides with respect to t. On the left, I have
Ah.
DDT. On the right, I have
Rick is on tonight, and he clarified it's him and his wife's Facebook account.
Okay, okay,
Rick, Eileen, together.
okay.
And their last name, Aaron.
Very good. On the right-hand side, I have a DD, sorry about that, a DDDT.
That's not a problem. I
That's
like
not a problem?
DDDT.
Okay, all right. And I happen to know that value because it says that sand is emptying out of this box at 300 cubic inches per minute. And so since it's emptying, I know that that means it's decreasing. I know that that means it's a minus 300. And I did a little bit of simplification and I included the units in there. I think that's correct, inches per minute. So that's a nice kind of problem to get you started. Now we have this sand, if you can picture this. No, I didn't draw a picture of this. The sand is falling out of this box and it's forming a beautiful canonical pile. You remember some people out there will certainly remember that there was a calculus problem, something like this a while back, an FRQ about this. At the instant when the pile is 23 inches high, the diameter is 16 inches, and the diameter of the base is increasing at a rate of 1.5 inches per minute. Let's see, find the rate of change of the area of the circular base at that instant. Yikes. Here's how I attack that one. Let's look at that first. Well, the first thing I need is an expression for, I think, the area of that circular base. So I went to pi r squared. And because I'm given information here in terms of the diameter, I felt it was easier to convert r into d's. So I know that the radius is the diameter over 2. That's where this comes from. And I did a little bit of simplification. Now, very typical related rates. I take the derivative of both sides with respect to t. Don't let me miss anything here, Curtis. dA dt. There's the pi over 4. Derivative of d squared. There's the 2d. And the derivative of d with respect to t, there it is again, dd dt. Sorry about that. Here, d is standing for the diameter.
By the way, I was just about to complain about your notation here, Steve, because I was going, we've already used this d. I needed subscripts. Mark Crowley likes your dd dt and your dd for the possibility. If you needed that. So, yeah.
All right. So it's standing for diameter down here. And I think I've got all these values if I've done everything correctly. I've got the diameter at this instant is 16. I think we know that the diameter is increasing at a rate of 1.5. I think it was inches per minute. And so that's a 3/2. I did a little simplification. I got 12 pi. I think the units there are inches squared per minute. Yep. That's an area increasing. So that's pretty cool. Part 2 is just a little bit longer, but similar. Here, let's see. We have to find the rate of change of the height of the canonical pile. Hey, I'm going to get an H in here. How about that? And I think in a lot of these problems, somebody always asks me this too. Do you have to memorize these expressions for volume? Well, it's good to know them, but frequently in these problems, they will remind you about what the volume of a cone is. So it's 1/3 pi r squared h. And here's what I did. Same thing, I wrote r in terms of the diameter. And I've got an expression over here for the volume of that cone. Okay. Let's see, I know how the diameter is changing. I need to find how the height of the pile is changing at this instant. All right, I got to take the derivative of both sides with respect to t. Got to be careful here. I have to use the product rule. So, okay, there's the pi over 12 out front. Derivative of the first one is 2d times dd dt. Did I say that correctly? There's the h.
Are we back to depth here?
What's that?
Oh, no, we're still on diameter, aren't we?
We're still on diameter.
Yeah.
D squared, derivative of h, dh, dt. That's the hard part. If I've done everything correctly here, I think I've got a lot of these values. I know the diameter at this instant is 16. I know it's changing at this rate. I know the height at this instant is 23. Whoops. There's the diameter again, 16, and this is the expression I have to solve for. So it looks kind of complicated, but I do indeed have one equation in one unknown, so I can solve for dH dt. I think this is the correct symbolic value. And in AP calculus lingo, there's the value 3 digits to the right of the decimal, I think rounded. And I think the correct units there are inches per minute. So I think, Curtis, that's a nice related rates problem. Forces the student to use the information given to them. In fact, switching from sort of R radius to diameter, that's a good solid problem. I like that one. Any questions at all on that one?
I just love the literal equation sort of work that you're doing here, right? And writing things in terms of each other. And I like this kind of problem. It's very interesting. Although I do have a question about how sand could really make the depth of that box go down like equally over time. I think we might get a hole in the middle and the sides would be kind of caving in. I don't think we would get a constant height, but maybe I'm questioning that.
There's always one who complains about that, isn't there? Yeah. All right, I'm going to do one more on particle motion, and then I'm going to turn it over to Tom for some technology to finish up this evening. I really like this one. This is a cool particle motion problem. Tom and I spent a lot of time talking about particle motion recently, and this one's got a parameter in it. This one I think was posted by Melissa Helbert, I think, if I've got that right. And a particle is moving along the x-axis so that anytime t, be careful here, greater than or equal to 0, its position is given by this expression, t e to the minus at. A is a positive constant. And I want to know at what time is the particle's position farthest to the right. Okay, so I got to think about this a little bit. And here's how I attack this one. I think what I need to do is to take a look at, okay, the velocity. Where is the velocity 0? Where is this particle changing direction? So I need to take a look at the first derivative. I need to take a look at x prime. Well, I've got a t e to the minus at, so son of a gun, I've got to use the product rule once again. Derivative of t is 1, leave the second expression alone. There's the t, derivative of the second expression, derivative of what's up there in the exponent, which is just minus a, and then that exponential expression, e to the minus at. And I apologize, I may have skipped a step or two in here, but what I did now is I factored this completely. So I took out an e to the minus at out of both of those terms, and I'm left with 1 minus at. Now you're right. I could factor out a minus 1 out of this term. For some of us, that makes it a little bit easier to see. But in my opinion, at least, that's factored completely. So I have to ask two questions. Where is that derivative equal to 0? Where is that derivative dne? Are there any places where it does not exist? Well, this expression here, as Tom pointed out a little while ago, that exponential expression, remember, a is a positive constant. That exponential expression is always greater than 0. This expression, I solve that, set it equal to 0 and solve, I get t equal to 1 over a. Are there any places where the derivative does not exist? No, there are none. And so I know, as you know, Curtis, I like to draw a sign chart. Not sufficient on the AP exam, but in my opinion, a very nice visualization and helps me write a sufficient conclusion. This is another little bit of notation, Curtis, that I add in my sign charts, and I don't think we've seen this before, but I'll put a little bit in here, a little plug in this. In this sign chart, I've added a left bracket over here, and the reason that I did that is because this problem says for t greater than or equal to 0, so I don't have to worry about anything down there to the left of 0. That's sort of my notation to tell me a little bit about the domain here. So I know that at 1 over a, the derivative is 0, so I've got that in. And now I've got to figure out the sign of the first derivative in those two intervals. Now, the way that I did this, the way that I thought about this is, well, think about going back to this expression. This one right here is always positive. I'll put a little plus sign under there. Think about taking a value that's very, very small positive, very, very close to 0. Well, this expression is going to be 1 minus that really small number, so it's going to be positive, making the product positive. Take a number over here. Think about taking a large value of t. 1 minus that, well, that's going to make this expression negative. The product would be negative. So thinking about this in terms of motion, my particle is moving to the right at t equal to 1 over a. It stops for an instant, switches, and moves to the left. Continues to move to the left out here as t goes out to infinity. So at what value is it farthest to the right? When t is equal to 1 over a. That's a nice problem. That's a really good problem. And I apologize if Melissa is listening tonight. I think this may have been presented in the form of a multiple choice question, but I kind of like the sort of exposition there and talking about that and solving that to see what's going on. Cool.
We had an interesting discussion go on in the chat about the cones a moment ago, and I just want to call it out that swapping, you could potentially swap out D for H because it makes similar triangles, which might be a more typical approach.
Well, I would argue that if you did that, you might lose your dH dt, and that's what it asked for in the problem.
Yeah. Okay. So I made it interesting anyway, so
okay,
I thought that was worth a bit of discussion there.
Very good. Tom, you all set?
Sure, I think
All
so.
right. There you
All
go.
right.
There you go, boss.
Well, I'm going to share a little bit off the TI-Nspire, and in fact, let me know if I've got the document up here. Great.
I can see it.
Yeah. Actually, I had the distinct pleasure of going to visit Steve last weekend, as a matter of fact, and we not just this past weekend, but a week ago last weekend, and we worked on some of the resources in Calculus-Nspire that are there for free for teachers. And this is one we were having just a blast working with. It's called Velocity, Position, Distance. And this is on the very topic of number 5 here, this motion along a horizontal line. So let me just show you how this file works. It's basically, it actually starts out with working with a given velocity. So that's a little bit different than the way this problem was posed. But along the way, Steve did develop a velocity function for this particular scenario. And I think his initial position was, if I just plugged in t equals 0, I got 0. So I think this was starting out at position 0. So I'm going to move this slider up here to an initial position of 0. And what I put in was a velocity function that would correspond to a equal to 1/5 or 0.2. So I put in a equals 1/5. And so we'll get e to the minus at, or negative 0.2t. And then here's my 1 minus at that you saw there. So that's my velocity function. And we'll go to the next page here, and this will set up. What it does is it graphs that velocity function for us, but it's also depicting the actual motion along the horizontal line as we advance time. Now let's think through. I think Steve said that his solution at t equal 1 over a is when this particle would get furthest to the right. It would have to turn around. That would be, let's see, 1 over 1/5 would be 5. So I would expect this particle to move to the right until t equals 5 and then turn around. Well, let's try it out. You can see it's actually, a lot of stuff is moving here on this page. If you look at the top, you see the particle actually moving. And you're also seeing the point along the velocity time graph. So let's see, I've got t equal up to 3.94. Okay, it's still moving to the right, but very, very slowly. You can hardly see the position changing at all. So I'm at t equal 5. Look at that. There's the velocity is exactly 0. Looks good. And now we should see, as I advance time, the velocity should become negative. It may be very slight. It is. You can see it's a very tiny velocity. And if you look at the particle up at the top, it is moving to the left now, but very, very slowly. That e to the minus at factor that's involved here, boy, that's really damping down the velocity big time. And so the velocity is actually very, very close to 0, but you can see that it's negative. This file is also showing the distinction between displacement, which would be the net change in position, and the total distance traveled, which is going to be the total length of the path traversed by the particle. That title page you saw there said part 2. If you're wondering about part 1, I'll bring it up real fast. What's kind of cool about it is the velocity function you can manipulate on the fly. It's piecewise linear, so you can make your own velocity function just by moving these vertices, and then you can see the resulting position. You can see it's actually dropping down, showing us a nice path. This is actually a little more interesting velocity function than the one from the problem, just because that one was damped down so much. So I think I've probably exhausted my time here. So let me get back to quitting the share.
Well,
Let's see.
Tom, that's a brilliant file, by the way. Thank you for sharing that. That's really cool. So as we get that file refined and posted up on the TI-Nspire calculus page, we'd be happy to share that. If you want that file for your Inspire classroom now, I think we can probably give you we'll call it a beta version of that TNS file. Certainly potential for revisions before we post it on Calculus Inspired, but I'd be happy to share that with you. If you email me, my email is curtis@ti.com. We'll put that in the chat here momentarily. And then yeah, so Tom, Steve, thank you a whole bunch. And actually to everyone who submitted questions on the Facebook page and the ones that Steve requested, and to all of the students who've joined us here from Miss Connolly's class. I've seen several students on here this evening, which is awesome, joining us here this evening. Thank you and welcome to the session, and glad you joined us. Be looking forward to hearing from you maybe over the next couple of weeks. We have another session here in about 14 days. We'll be back here on Monday the 15th to answer more of your questions, do a little bit more calculus and technology demonstrations, which is great. So thank you very much. Really glad that all of you joined us this evening, and we'll see you in a couple weeks. Good night.